Number 41. For the following exercises, find all complex solutions, real and non-real. Of course, real numbers are a part of the complex number system. So real and non-real numbers form the complex numbers. So here's our equation. It's got a leading coefficient of 1, so all we have to do is consider the factors of 26, or rather negative 26. It really doesn't matter the sign because we're going to use both signs anyway. So the possibilities for P over Q. So plus minus 1, plus minus 2, plus minus 13, plus minus 26. Alright, so to save time, we jump right to the one that works. That would be positive 2. There's our zero remainder. So we can factor this polynomial in this way. You've got the 2 there, x minus 2, times what we have here. That would be 1x squared minus 6x plus 13. X squared minus 6x plus 13. Alright, now this one can't be factored over the integers, alright? So also if you look at the discriminant, b squared minus 4ac, you'll see that it's negative. So what you're going to get are non-real roots out of this one. Alright, so we have one real root so far, that would be x equals 2. And we'll have 2 non-real roots, so a total of 3 roots, of course. So we're going to solve this quadratic for x and use a quadratic formula. So that's negative b plus or minus square root of b squared minus 4ac. all over 2a. Alright. So that would be 6 plus or minus square root of, that's going to be 36 minus 52, which is negative 16, under the radical, over 2. And that's equal to 6 plus or minus, and this is 4i, over 2. You can factor 2 out of the numerator. So that's 2 times the quantity 3 plus or minus 2i all over 2. Now we can cancel the 2's out. And finally you end up with 3 plus or minus 2i. Alright, so the zeros are 2, 3 plus 2i, 3 minus 2i. Number 43. So here's our equation, and we'll put the possibilities for P which would be the factors of 10, and the possibilities for Q, which would be the factors of the leading coefficient, 3. And so for 10 we've got plus minus 1, 2, 5, and 10. And for 3 we've got plus minus 1, plus minus 3. Okay, so possibilities for P over Q then are rational roots here. Well, let's see, we've got plus minus 1, plus minus 1/3, plus minus 2 over 1, which is 2, plus minus 2/3, plus minus 5 over 1, or 5, plus or minus 5 over 3, plus minus 10, plus minus 10 over 3. Okay. There's a lot of possibilities, so jumping right to the one that works, it's negative 2/3 is the first one I came across. And yes, I did go through all of them. As you can see in my notes, if I can straighten them for you. I don't know why. I could have looked in the back and just saved myself some time, but hey man, this is like good old days when I was a student. So it's kind of like reliving the past. Makes me feel young, you know. So I don't do that all the time. Because it gets a little old, but you know, when you're a student, you should practice it. And then after you've practiced it and start teaching it, and then you retire, you can be like me and just kind of do what you please, right? So there's your 0. Alright, so this polynomial up here can be factored as x minus negative 2/3 times 3x squared minus 6x plus 15. Let me write that out up here. X minus a negative is x plus 2/3, and 3x squared minus 6x plus 15. Now I can see there's a common factor of 3 in this second polynomial here, so we can move that out and multiply it by this, because that'll clear that fraction when you multiply that by 3. So with x plus 2/3, 3, and then factoring out the 3, you get x squared minus 2x plus 5. So that simplifies that quadratic, which we're going to have to solve in a minute. Multiply that 3 through the first one, you get 3x plus 2. And then x squared minus 2x plus 5. Alright. So it turns out we cannot factor this quadratic over the integers. Alright. Again, you can check the discriminant as a quick way of doing that. If you try factoring it, you're just going to find you can't do that. So when you can't factor it as usual, you just go right to either the quadratic formula or completing the square. Alright, so we'll just use a quadratic formula. X equals negative b, that's negative of negative 2, plus or minus square root of b squared minus 4ac, and we're doing this one here. All over 2a. You say that often enough and you'll never forget that formula. When you're a student, just say that all the time. Whenever you use it, just recite the quadratic formula, and when you're old like me, you'll still remember it. I don't know if it'll be any use to you, but you'll still know it. So this is going to be 4 minus 20 under the radical, all right? And that's equal to negative 16 over 2. And let me just keep going horizontally here. That's going to be 2 plus or minus 4i all over 2. And you can factor a 2 out of the numerator like we did in the last problem, number 41. Cancel the 2 down here with a 2 up there, and then that leaves you with 1 plus or minus 2i. I will leave the details to you, which by now should be pretty automatic for you. So we've got a root negative 2/3, and we've got 1 plus 2i and 1 minus 2i. So negative 2/3, 1 plus 2i, 1 minus 2i. Number 45. So here's our equation, and we'll write possibilities for P over possibilities for Q. Should have used ditto marks, but oh well. Alright, so the factors of 17, that's easy. Plus minus 1, plus minus 17. And then possibilities of factors for 2 are 1 and 2, plus or minus. So the possibilities for P over Q, oops, there we go, P over Q, 1 over 1, that's 1, 1 over 2, that's 1/2, 17 over 1 plus or minus 17, 17 over 2. Okay, so it turns out that negative 1/2 is one of the things that'll work, one of the numbers that'll work. Okay, so this polynomial can be factored as x minus negative 1/2 or x plus 1/2. And what we have here is 2x squared minus 4x plus 34. And we can get a common factor of 2 out of this quadratic, bring it outside. And if you multiply the 2 times this one, you're going to clear that fraction. Okay, so multiplying the first factor there by 2, we get 2x plus 1. And then x squared minus 2x plus 17. So that common factoring will save us a little trouble when we solve that for x. And we can't factor this one over the integers, so we can use a quadratic formula, or again complete the square if you wish. And what you're going to get is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Alright, so by now that should be a mantra in your head. Alright, so it's like a tune that keeps coming back in your head and you can't get it out of your mind, right? I'm going to skip a few steps here. Because if I keep going over these basics in detail, you know, it's going to take me forever to go through these problems, right? So I have to expect you to learn the basic details sooner or later, and then we can save some time. Not trying to rush you, but you know, that's time is of the essence. As they say. So this can be written as 1 plus or minus 4i. Okay, so we've got the roots -1/2, 1 plus 4i, and 1 minus 4i. Okay, here we go, number 47. For the following exercises, use Descartes' rule. Descartes' rule, right? Yeah, that's a French name. Famous mathematician and philosopher, Descartes. From him we get our Cartesian coordinate system, XY axes, right? And he basically tied geometry together with algebra. That's Descartes. He did a lot of other things too. But anyway, Descartes' rule of signs, you can also call it, to determine the possible number of positive and negative solutions. Then graph to confirm which of these possibilities is the actual combination. All right. So we have f of x equals x to the 4th minus x squared minus 1. So, can we use Descartes' rule of signs? Well, the condition is f of x has to have real coefficients, which it does, and a non-zero constant term, which it does. So Descartes' rule of signs applies to this, all right? And what do we have? We go from positive to negative. That's one change of sign. I'll just show it like that. That's a variation there. So check. And then from negative to negative, which is not a variation. So we just have one variation of sign. So we have the number of positive real roots of f of x is 1. Let me write positive real roots is 1 or less than 1 by an even number like 2, 4, 6, and so on. All right, well, you can have 1 or 0, obviously. You can't have 1 and then less than 2 less than that. Okay, that's getting into a negative number, which doesn't correspond to reality here. So just 1 or 0 positive real roots. All right, 1 or 0. Now we try f of negative x. So don't forget those parentheses. In case you're not clear on why, I mean, what's the difference between this and this? Okay, well, probably better to use x to the 4th, since that it's already a positive here. So let me do that as an example. What's the difference between those two when we write f of negative x? Well, this is equal to -1 times x to the 4th. I'm going to need space here. And that equals -1 times x to the fourth, negative 1 to the fourth, rather, x to the fourth. Right, you have two factors in parentheses raised to a power, x times y to a power, that would be x to the power times y to the power, right? And so negative 1 to the fourth is positive 1, and then we just have x to the fourth. But what is this? Negative x to the fourth without the parentheses. That equals negative 1 times x to the fourth. Right? And by order of operations, you do the power first, and then you multiply. So it's just going to equal negative x to the fourth. Alright? And so that 4 does not apply to the negative 1 because of order of operations. But when I write it like this, it does. Okay? So notice the difference. That could be a big difference, especially when you get into calculus. All right, you get into some long computations. That's going to really destroy your answer. Okay, so yeah, there is a big difference. So keep those parentheses where they should be. All right, so this is going to be x to the fourth minus x. That's going to become just positive x squared, which is just, you got the minus there, minus x squared minus 1. So we're going from plus to minus, that's one variation. Check. Minus to minus is not a variation, so it's just one. So f of negative x has one variation of sign. So again, there's either one negative real root or less than 1 by 2, 4, 6. Well, obviously, it's not going to be less than 1 by 2, so it's just 0. All right? So we've got 1 or 0. So we can make a little table of possibilities. The total number of zeros or roots, positive real roots, the negative real roots, and the non-real roots. So it's a degree 4 polynomial, so that means we're going to have total number of 4. Okay. Roots. So we could have one positive, one negative real, like we see here with Descartes' rule. And that means there's 1 plus 1, that's 2 real roots. There's going to be 2 more to make 4, so that would be 2 non-real roots. All right. Now, non-real roots always occur in conjugate pairs. If you have something like a plus bi is a root, a minus bi will also be a root. These are conjugates of each other. That's what they call conjugates. All right. So non-real roots in these always occur in conjugate pairs. All right. So if you have one non-real root, you're going to have another one. All right. And they're conjugates of each other. So there are always good. If you have one, there's going to be 2. Right. If you have at least one, you know there's at least one. You know there's going to be another one. Okay. So we could have this 1 positive, 0 real, and well, that means 1 plus 0 is 1 real root, and there can only be a total number of 2 in this, 2 non-real roots. You could either have 2 or 4, but then that would leave that out. All right. So you could have this, or you could have that. All right. Now, this column and this column would be the only possibilities. All right, these don't add up right. Okay, 1 plus 2, 3 roots total. All right, they don't add up. So we're going to have to go with one of those two. Okay, and if it's this one, it's not even going to touch the x-axis when we graph it. Okay, so let's take a look. When you graph this polynomial up here, here's what I got. As you can see, it does cross the x-axis twice. And we have a negative real root. Oops, sorry, that's a negative. I have to look at it the right way here, and that's a positive there. All right? Okay. Oh, and what are the 4 roots? Well, you could use a computer if you wish to solve this. It's 1/2 times the square root of 2 plus 2 squared of 5. These are irrational roots. That's about 1.272, and you have -1/2 square root of 2 plus 2 squared of 5, which is -1.272 about. And there are 2 non-real roots. 1/2 square root of 2 minus 2 squared of 5, which is about 0.786i, and -1/2 square root of 2 minus 2 squared of 5, square roots within square roots, which is about negative 0.786i. So we have 2 non-real roots, 2 real roots on that one. And of course you only see these 2 real roots on the graph. Alright, you're not going to see those on the graph.